Hello, I'm Dragan Maksimovic, Professor of Electrical Engineering at the University of Colorado Boulder. Here we will be talking about modeling of losses and efficiency in DC-DC converters, or more generally in power converters. So we want to see what are the factors that affect efficiency of switching converters and how efficiency can be improved. Let's start with the circuit diagram of a simple buck converter with silicon power MOSFETs. We have talked about the implementation of the switching action using power semiconductor devices. We now want to see what is the effect of having that implementation together with practical component choices for the inductor and the capacitor on the overall efficiency of the converter. So first of all, to remind you, a power MOSFET behaves as an open circuit when it's off, or as an open circuit as a small on resistance when it's on. And the on versus off state is dictated by application of the control gate to source voltage above or below the threshold. So this model of the power MOSFET is going to allow us to develop a model for a particular loss mechanism is called conduction loss. So an average circuit model is shown here, where we have either one of the two MOSFET turned on, represented by an on resistance R-on. We mentioned that when the MOSFET is turned on, it's represented by a small on resistance. The switching action results in a controllable voltage source that's proportional to the duty cycle of the switch, and the remainder of the circuit consists of a winding resistance of the inductor and a load resistance at the output. So power delivered to the load resistance R0 is the useful power, and we want to see how much smaller that useful power is compared to the power that is taken from the input source. Here is just a summary of what are the circuit elements included in the average circuit model, and those include a duty cycle of the switch. R-on is the power MOSFET on resistance, RL is the inductor resistance, and R0 is the load resistance. It's a model of the load. All right, so now we are in position to estimate the loss and calculate the efficiency of the power converter. The conduction loss is going to be, from the circuit model shown here, is going to be proportional to the sum of the series resistances that include the transistor on resistance and the inductor winding resistance, and the square of the output current, right? So I0 squared. So this is the total conduction loss. Conduction meaning it's loss because of the current flowing through the components in the circuit. The output power, on the other hand, is equal to R0, the resistance of the load, times the I0 square. Now, these two expressions here can be used to compute the efficiency of the converter as the ratio of the output power times over the input power, and the input power being the sum of the output power and the loss. And the simple algebra results in efficiency expression that's 1 over 1 plus R1 plus RL over R0. You can see if these components were ideal and we had 0 on resistance of the power MOSFET and 0 winding resistance, efficiency would come to 1 or 100%. The larger the on resistance and the larger the winding resistance are, the lesser the efficiency of the converter is going to be. So here is that expression again. To improve efficiency, we want to choose a power MOSFET or a GaN transistor with small on resistance and an inductor with small series winding resistance. Because if these components resistances are much smaller than R0, that implies that the efficiency can approach 100%. And we will see a little bit later on some practical examples of how close to 100% we can get. Now, conduction loss is just one loss mechanism. There is unfortunately another loss mechanism that is in power electronics practice referred to as being a switching loss. What is the switching loss and where is it really coming from? So when we look at the practical circuit of a power converter, such as the simple buck converter shown here, recall that we have the switching action implemented by having these two switches, the main control MOSFET and the synchronous rectifier operating in a complementary manner. So if you look at the voltage and current waveforms across, let's say, one of these components, this Q1, here we have the current going through 1 being equal to the inductor current when the MOSFET is on, and that is the current that is going to be determined by the inductor current during the time interval between 0 and DTS. And when the MOSFET is off, then the current is equal to 0. Similarly, the voltage across the MOSFET is going to be equal to very close to 0 when the MOSFET is turned on, and it's going to be equal to the input voltage when the MOSFET is turned off, because the complementary MOSFET is on during that period of time. So if you look at the product of the current and voltage of that particular switch, that product should ideally be equal to 0 all the time. It's not equal to 0 because we know that we are going to have conduction loss here because of the voltage drop across the on resistance, but it's going to be very small all the time. Unfortunately, the transitions that are shown here as instantaneous, this transition here and this transition here, they're not really instantaneous, and the product of voltage and current during transitions can be substantially different from 0. And that really is the origin of the switching loss. So looking at that a little more carefully, let's suppose that we look at the turn-off transition of the main control MOSFET. So this is the current dropping from a high value here down to 0, and at the same time, or nearly the same time, the voltage increasing from 0 to the high value here. If you expand the time scale, if you look at these waveforms on an oscilloscope and you expand the time scale to see what is happening during this transition, you may see something that approximately looks like this. You have the voltage across the switch terminals between drain and source increasing gradually from 0 or close to 0 to some maximum value equal to the input voltage, and then the current dropping down gradually from the maximum value equal to the inductor current down to 0. During that transition, and this is on a time scale that would be maybe tens of nanoseconds up to maybe hundreds of nanoseconds for a power MOSFET, the product of the voltage across the MOSFET and the current through the MOSFET is not equal to 0. And in fact, it actually instantaneously gets to a very high value. So given that the product is not equal to 0, means that there is an instantaneous power consumption during the turn-off transition, and that instantaneous power consumption results in a chunk of energy, the area under this curve, that's equal to the energy lost during the off transition for that particular MOSFET. Now, each switching transition and each switching device is going to have some amount of energy lost during a switching transition, and the sum of all these energy loss during switching transitions amount to what is called a switching loss. So a summary on the switching loss, the mechanisms are much more complicated than what I'm explaining here very briefly. They involve limited turn on and turn off speed of power semiconductor devices. There is a need to supply charge and remove charge from the semiconductor regions in a more complex physical view of the devices. And there are also parasitic device and circuit capacitances and inductances. The charging and discharging of those also involves an amount of energy lost in each switching cycle. So the total switching loss energy is a summation of the energy loss during turn-on transition and turn-off transition, and this is a chunk of energy that is lost in each switching period. The total energy lost in each switching period depends on the switch type, depending on which particular device you're using, or whether you're using a silicon MOSFET or a gallium nitride or a silicon carbide device. You're going to have different loss mechanisms involved, and the net loss will be different. Also, that loss depends strongly on the operating conditions. Depends on how large the voltage and currents are switched. But overall, in a big picture, if the amount of energy is lost in each switching cycle, how many cycles per second we have is determined by the switching frequency. The total switching loss is going to be proportional to the switching frequency. And we can inevitably see here that the higher the switching frequency of operation is, the larger the power loss is going to be, which then requires a question of why are we not switching at very low frequency? And the answer to that is going to be clear in the next segment, where we talk about the size of the passive components. The higher the switching frequency is, the smaller those components are, and that's going to be the trade-off that we are working on when we design practical switching converters. One thing that we want to note here immediately is that the switching losses are lower with wide bandgap power transistors, which means that wide bandgap based converters can operate efficiently at higher switching frequencies, which can again result in smaller size of the power converters. As a summary, when we talk about losses and efficiency of the power converters, we want to mention that there are a variety of loss mechanisms in switching converters. The two main loss mechanisms include conduction losses due to on resistances of power semiconductor components and series resistances of passive components and circuit interconnects. Switching losses are due to limited turn-on of speed of power semiconductors, stored charge in semiconductor regions, and parasitic device and circuit capacitances and inductances. Importantly, switching losses are proportional to the switching frequency. There are also other losses that I haven't mentioned explicitly here, such as core losses in magnetic components, and series resistances in magnetic components also have dependence on the switching frequency because of uneven distribution of current through the windings. Practical power converter designs are complex. They involve careful design trade-offs, including selection of converter circuit configuration, components, selection of switching frequencies, there are a variety of operating modes, and many other aspects. So power electronics is a discipline that involves a significant knowledge base and experience and practice to accomplish effectively.